Welcome back, everyone. This is Lecture 10b, Calibration and Characterization. I'm Jonathan Baker. In this video, I'm going to talk about several experiments which are used to perform calibration or characterize device noise. That is, how do we obtain those values that we used in the previous lecture to perform error-aware compilation mitigation? So, for example, we had suggested we knew how long gates were going to take, and we knew the coherence times, the T1 and T2 times of our qubits, and we knew approximately how well gates performed on edges were going to perform, or how good they were going to be. So the idea is that we want to find some simple, scalable experiments or protocols that we can run to characterize our qubits, or our couplers, or any other component of our hardware, so we can perform high quality operations on them. If we use stale or generic control of our qubits, then we may not get the best performance out of the device because we expect that the system parameters to drift and fluctuate over time. And so we want to make sure that when we run a program on the device, we get the best possible result we can out, meaning that we want well-calibrated pulses or control of our system. And if there is some error that's part of the system, we want to be able to maybe target it with specific mitigation techniques and not attempt to mitigate errors that aren't actually even present in our system. So performing these steps of calibration and characterization are really important. I want to talk about a few examples of those. Okay, so first is calibration. And for today, I'm going to focus on superconducting qubits like those of IBM, but there are similar types of experiments, if not the same, that would perform on other types of systems like ion traps or optical qubits. Ideally, our qubits operate at some frequency, which specifies the difference in energy between the ground and excited states of our qubit. So for example, we're used to labeling our two energy states of our qubit as 0 and 1. And we want to know what is this frequency, but what is the energy gap between these two states of our system. Knowing what that frequency is crucial for us to perform operations with this qubit accurately. So we want to find whatever this F is. Many physical qubit implementations are actually QDITs, or a D-level system. So instead of having just two levels, we'd have 0, 1, and then 2, etc. This is a D-level system versus a two-level system. But ideally, in most cases, current systems are optimizing for these lowest two levels. And we do actually want to, these states are usually present, and we do want to avoid any of our state leaking, a leakage error, where the state actually becomes a two-state on accident. And so what happens is that the system is built in with some sort of anharmonicity, meaning that the gap between 0 and 1 is not the same as the gap between 1 and 2. And so if we know what the energy is between 0 and 1, we can force transitions only between those two states and not worry about things happening between 1 and 2. Of course, that does happen sometimes. We usually have an estimate about what this frequency is, what this spacing is, but we want to be as precise as possible. And so one experiment that we can do is actually to calibrate that frequency difference, or the energy difference. And so we're going to sweep across different frequencies and build a pulse sequence, some Gaussian analog pulse that's applied to the system. And we're trying to excite the ground state qubit into the excited state, from 0 to 1. And so what we obtain is a curve. If we do this many times and we measure the outcome, is that we get on the x-axis is our frequency. So we're trying to find what the frequency is. And on the y-axis is some signal that we're measuring. And what we get is some curve that might look like something like this, centered around the frequency of our qubit. And so by fitting, what we'd actually get is a sampling of points along this curve. And by fitting those samples, we find a curve that looks like this, and then we can predict what the frequency of our system actually is. So then, how do we use this information to actually do something useful? This just tells us what this energy splitting is, but that's important to calibrate something like an X gate. So let's do a calibration of an X gate. Because we want a precise control so that we don't only maybe do a partial rotation around the x-axis and then end up with something like 90% occupancy in the one state after the supposed X gate. We want to get as close to 100% occupancy in one state. Or to the back, or the other way, where if we are all in one, we want everything to return back to 0. Okay, so the strategy here is called to obtain rabbi oscillations. And so what we're going to happen is we're going to apply a pulse, and we're going to watch the state oscillate between the 0 and the 1 state and back again. And using this curve, we can obtain what amplitude our pulse should be executed as. Okay, so the experiment is similar to before, but this time now we're going to sweep across amplitudes. So as a reminder, when we're executing pulses on the device, we have some curve that looks like this, some analog pulse sequence that's being played on the device. And at each step, there's an amplitude. And we want to find what amplitude this pulse should actually be in order to accurately move our system from 0 into 1. And so what we do is we sweep across amplitudes. So now we have a curve that looks something like the x-axis is amplitudes. And again, on the y-axis, it's the signal that we get after measurement. And in this case, we're getting something that's much more oscillatory. So we get the points along this curve. And again, if we fit this to some curve, for example, then we can find out the amplitude that we need to accomplish a pi rotation around the x-axis. So looking at the period of this curve from this experiment. So if either the frequency, the first thing we found, or the drive amplitude are miscalibrated, then what we end up is with single qubit gates that have error in them. And we'll mention how to recover how good an operation is shortly with a different type of experiment. But for now, being sure that what we've calibrated or characterized about our qubits is really important to getting good high fidelity operations. Okay, so let's before we go into like how to characterize gate error, let's talk about a fairly simple experiment which is used to measure the coherence time. So we'll talk about both T1 and T2 times. So this experiment is the first one we'll talk about is T1, and this experiment is very straightforward. So the T1 is measuring how long it takes an excited qubit in the 1 state to fall back down into the 0 state, which happens naturally over time. So pictorially, if we start here in the 1 state, and as time passes, we expect that some of this population will have fallen down into the 0 state. So this is like over many samples, that now we have like some in the 1 and some in the 0. And if we wait even more time, a long time, then we'd expect everything to fall back down into 0. And the rate of decay at which this happens would refer to our T1 time. Okay, so this experiment would follow exactly this example here. Is we would excite the qubit with an X gate to the 1 state, and then we simply wait. So we perform this many times. So we'll obtain a plot with this experiment where this is the time weighted. So we're performing this X gate. So let's draw a circuit example. We apply X gate to our circuit, and then we wait some amount of time t here before measurement happens. And that's it. We just vary this t, and that's exactly what this x-axis is capturing. And then again, the y-axis is something like it. I guess you could measure it as the amount of state is left in 1. And you'll get a curve, you'll get points along a curve like this. And we can fit that data. And then essentially what we'll find is this is it decaying in some exponential way, and it directly gives us the T1 from the curve that we fit to this. The form of the curve involves the term T1. Because that's very simple. So we understood what happens to the state, and we found an experiment that essentially does exactly that to figure out how fast is this decay happening. Okay, so what about for T2? So we'll just draw it in the bottom right here. So T2 this time. It's very similar, but instead of falling from 0 to 1, we're seeing how fast we rotate around the midpoint of our block sphere. So we begin by applying, instead of just this x pulse, we do a pi over 2 pulse. This is an Rx of pi over 2. And then we wait some amount of time. So we'll just draw the circuit diagram for this one. We wait some amount of time. We apply an Rx, or an X gate, or a full pi rotation. Wait that same amount of time, from our Rx pi over 2, and then measure. So very similar experiment. But this time this whole thing is actually equal to the identity, right? 2 X gates, or 2 Rx of pi's equal the identity gate. But we're varying this t, the amount of time we wait between this basically flipping of the state. And then we obtain a very similar curve to before, where x-axis is this time, and y is here we'll just call it signal. And we get some other curve that measures the t2 time from fitting it. Okay, so similar experiment, it's just that now we have a little bit different how the time is actually being applied in this case. Okay, so the next thing I want to talk about at a very high level is what's called tomography. So say we have some quantum state or gate, or even some full circuit, and we want to know what does this state actually look like, or what operation did this thing actually perform. So there's a mismatch between what we write down in our circuit and what's actually being executed on the device. And the unitaries that are actually being applied and what we think that's being applied may be different. And the idea is, what is the thing we actually applied? We don't know for certain, because all we get out at the end is a distribution of answers of classical bit strings. And we want to reconstruct what actually happened from those results. And that actually involves many experiments altogether to reconstruct the state really precisely. So the idea of tomography is solving that experiment. So what actually happened? Or what is my actual state? So part of the problem here is that many possible operations or states can actually result in the same measurement outcomes, but internally there is some difference. So for example, the phase might be different between two states. The plus state and the minus state both evaluate to the same outcome distribution, but they're two different states for computing purposes. They do different things. And so we want to actually construct what is the exact form of the state, rather than just looking at what the outcome is. And we do this because we want to know that our device is performing the operations we think they are, and not something that looks the same but isn't actually computing the same. Okay, so there's a couple different types of tomography. The two here I'm going to emphasize is what actually happened refers to quantum. We can solve this by quantum process tomography. And the idea here is given some circuit, reconstruct a description of what, like quantum channel, so how it applies to density matrices, so we can know exactly what's happened, what the circuit's actually doing. And the second is solved by quantum state tomography. These two processes are both expensive and require many runs of the circuit to accurately reconstruct the state of a unitary or the state itself. However, they can accurately assess what errors are in the system. I don't really want to cover too much about this because it's not practical from a scalability standpoint to perform full tomography of a device, especially as we get to larger devices in the near future. If we wanted to accurately characterize maybe one edge or one qubit of the device, this might be useful. But there are other alternatives that we can use to get an approximation of things happening without having to do full tomography, which tends to be expensive. One other note is that these types of experiments are sensitive to what are called spam errors, which are state preparation and measurement. So basically, how do I start my circuit, and how do I recover the outcomes at the end? A third type of tomography is called gate set tomography, and so these types of spam errors can be accounted for in that type of tomography, but the scaling of that is much worse, and so as our systems get larger, it becomes infeasible to expect to do tomography on our system. But sometimes it's necessary. It kind of depends. Okay, the last thing I want to talk about is a scalable alternative to tomography, but it only partially characterizes the errors. It's randomized benchmarking, or often referred to as RB. The RB protocol consists of several steps. The first is to generate what are called RB sequences. So what we want to do is we want to, form RB sequences. Okay, and so what this involves is that we want to uniformly at random sample Clifford gates. So for example, gates in this set we've seen before are X, Y, so all the poly gates, S, but our Hadamard is also here, and our CX, so these things are all the Clifford gates, or some, and generated by these things. And here we want to consider the Clifford gates on n qubits. These are just for maybe 1 and 2 qubits, so there would be a more generalized form of these things. So more precisely, we're going to form a circuit that consists of these things. So say, for example, we generate a circuit that looks like this on 2 qubits. And these are all these gates are randomly sampled. And we'd form many of these sequences. The one sort of restriction on what you generate is that ultimately this whole thing needs to be equal to the identity. So really we're basically doing nothing but by doing a bunch of gates to do nothing. Okay, and so the second step would be to execute these gates. And then third would be to measure the results and get some metrics about what's happening. So metrics, I'll just say this step. So of course we expect for the identity that all of our outputs end up back into the all 0-bit string, but in practice, because of noise, which is exactly what we're trying to characterize here, this won't be the case, and instead we'll still get a distribution over answers. Most of it will probably still be in the all zero case, but some of it will not be, and that will basically tell us the average error of a Clifford gate. Okay, so the step 4 then would be to average the measurements to obtain the sequence fidelity. So let's write average sequence fidelity. And this basically tells us what is the chance of any one of these Clifford gates having an error on them. Okay, and so then 5 would be to repeat for many k. Okay, and so in step 1, we're generating an RB sequence of a fixed length k, and then we want to do this for many possible k's to get an accurate representation of what this average Clifford error is going to be. So we want it to. So we expect for some amount of error that as the sequence gets much longer, the errors accumulate and we get some decay in our total success rate. Okay, so this is very scalable, and this gives us this average Clifford gate error rate. And then this can be used to approximate what is. So if I have many 2-qubit gates, we can use this to approximate our 2-qubit error and our 1-qubit error. Okay, so let's talk about scalability of randomized benchmarking. So this only requires us to take sequences it does depend on n, but all these gates will be easy to execute, or relatively easy to execute. But in practice, it's not super efficient to maybe characterize the whole device all at once. And instead, it's more common to perform RB on each of the connected pairs of device. So if we recall, we have our device, our nice superconducting device with edges and qubits. And essentially, we'd want to perform RB on all of the different edges by themselves. So we'd perform all of these on 2 qubits, at most 2 qubits. And then we would get an approximation of each of those error rates. Okay, so in this video, we've covered some very basic experiments that can be run on devices. You can even take these experiments yourselves and go and try to run them on an IBM device. And so we've used these to study how gates are executed on the device. How do we figure out what our qubits look like, how much energy is between their ground state and their excited state, and then how do we use that information to execute gates via pulses to actually drive transitions between the states. This is all very high level and scratching the surface. There are other experiments and protocols one can use to more accurately assess exactly what's happening in the quantum system. So, for example, you could go back and look at tomography more deeply to understand your system. And this is really important when you're trying to design error mitigation strategies that are targeting specific types of errors. So if I know that I only have a certain type of coherent noise, which I've characterized via tomography or something, then I can try to develop strategies that specifically target that type of noise that I know my system has, rather than some generic protocol.